Okay, hello. I'm starting, huh, Dipsika?
Yeah, then you can start.
Okay, fine. So, hello everyone. Good evening. So, first of all, let me introduce myself. As you all might know, don't know me, I guess so. So, my name is Munmi, and I am in my final year dual degree course. So, I think this is enough for this time being. So, okay, let's move to the presentation. First, I just want to clear one thing that I'm not going in detail of the Mesoporous silica. That is my topic of my talk. Cause I know because many of you are guys are in first year only and you don't know about much about ceramics. In fact, you don't know nothing about ceramics. So just talk briefly about Mesoporous silica porous ceramics. And I am also a student like you guys, so I too don't know much about in detail of Mesoporous silica, or I'm not aware of something. So just I want this session should be an interactive session. Let's hope for the best, and let's move to the presentation. So this presentation is basically oriented towards the first year and second year students because it's too simple and very introductory part. I just wanted to give you some brief introduction, brief about Mesoporous silica and porous ceramics. So uh, uh, let's start our presentation. Today my topic of my presentation is Mesoporous silica. Am I audible now?
Yes, ma'am, you are audible.
Okay,
Yes,
okay,
ma'am, you are
fine.
audible.
If you have any question, then you can ask, and okay, we'll talk informally later after my presentation. uh, let's finish my presentation first. Okay. So topic of my presentation is Mesoporous silica, which is a kind of or type of porous ceramics. So basically okay. Okay, basically outline of my talk is porous ceramics. I'll be covering some portion of porous ceramics. Here I will give some introductory part and application and manufacturing part of porous ceramics. And then I will move to Mesoporous silica, which is a type of porous ceramics, a special type of porous ceramics. And there I will cover introductory classification and its unique properties, application and synthesis part. And after that I'll just touch some few points of future scope of Mesoporous silica, what people have worked on Mesoporous silica and what can be done in future about that only. So next is first of all, what are porous ceramics? Actually, in the ceramic field, porous ceramics is also termed as cellular ceramics, and we have many people have talked on the dense ceramics, and you guys also generally talk about normal dense ceramics, but porous ceramics is also a and very important domain of ceramics, which have very important application in the different fields. So porous ceramics are basically combination of two phases. One is continuous solid phase and another is porous phase. Okay. Okay, continuous solid phase and the porous phase. So, continuous solid phase basically forms the porous frame, or which is also known as strut. And I'll cover this part later. I'll show you one picture, then you will be clear on that. Then it will have a lot of pores in it, and that pores may be filled with gases or liquid. Basically, during manufacturing of the porous, you have will be filled with liquid or gases, basically liquid. Then after removal of that liquid by any chemical method or heat treatment, then we will get the actual porous structure. So now there is a question: is every material with pores are referred as porous? It is a very important question for ceramics, ceramic material especially, because as you all know that all dense ceramics are not 100% dense, because it will contain some portion of voids or pores in it. So it is not 100% dense. So should we consider that also at porous ceramics? Actually, that is not the case. We cannot consider that dense ceramics with some pores as impurity phase as porous ceramics. We cannot consider that because there are two essential characteristics that we should consider before referring a material as porous material or porous ceramics. First of all, it should contain a lot of pores, and generally it should be in the range of 20 to 95% of pore. Means it should have very large number of pores. So next is pores are generated to achieve better materials performance. Means see, we have in porous ceramics, we are deliberately, we are intentionally generating some pores into the material to get much more better performance of the material, and to use the material in a particular application. As ceramic materials may contain pores, voids as impurity phase or as defects, they may contain, because it is the inherent property of ceramics that it may contain some amount of impurity as voids. So but that voids or that cracks actually degrade the material's property. It degrade the material's performance, so it cannot be considered as porous materials or porous ceramics. So these two are the essential characteristics that we should consider before referring to a material as porous material. Next, these are the actually simple properties of porous materials or porous ceramics. That it have high surface area, very high surface area, because as of course it has a lot of pores, so of course it will have a high specific surface area. And next, it will have low density. Of course, various reason that it will have very low mass. Next is high permeability. It is basically due to high permeability, as I think you all know that the permeability term, and permeability term is related to the connecting pores and open pores. I'll go to that part, open pores or what is connecting pores. Basically, if your material have connecting pores or open pores, that material will show a high permeability, and high permeability is basically important for membrane purpose or any absorption purpose, like that. And next is high thermal insulation. um, it is an obvious reason, because as we all know that if a material is porous, it will not conduct heat, because it contains a lot of pores which contain basically air, and which is a bad conductor of heat. So it will act as a thermal insulator. So at last is high thermal and chemical stability. This is a property which is specifically for ceramic material, porous ceramics. These are also applicable for any other porous metals or porous polymers. But this point, high thermal and chemical stability is a inherent property of ceramic material, because as you all know that ceramic materials are high temperature materials, and it has a very high corrosion resistance, a high chemical stability. So this is an inherent property of porous ceramics. So next is everything clear to everyone? It is quite introductory part or simple. Hello.
Clear day.
Okay. Let's move to the classification part. Here are the some portion. So porous ceramics can be classified into different types based on pore geometry or pore size. So see, it is a general classification of all the porous materials, including metals, polymers, and ceramics, because they may contain low porosity, middle porosity, and high porosity. These are according to the amount of porosity present in that material. 20 to 30%, 40 to 50, and greater than 60. These are the general classification for all the materials. But for the ceramics, these are the two basics classifications. This is based on the shape of the pore or geometry of the pore. This is honeycomb ceramics, and one is ceramic foam. And these two are the based on the geometry of the pores. And this ceramic foam can be subdivided into two: open cell or closed cell. So finally, first of all, honeycomb ceramics. What is honeycomb ceramics actually? Honeycomb ceramics actually contain some channel-like pores. Means the pores are not connected to each other. They are extended in two direction only. They are 2D pores. Means here you can see this. Wait a minute. You can see this picture. These are the honeycomb. Actually, the cross section, actually it is named as honeycomb ceramics because the cross section of this material is looking like honeycomb. So say these are the pores, and these are separated from each other. They are not connected, and they are extended in one direction, two direction, and they are like channel legs. All the pores are channel legs, and they are very regular and very ordered pores. So these are the honeycomb, and it may may have different shapes like a square or circular, depending on the mold we use during the fabrication. And next is ceramic foam. Ceramic foam is that type of porous ceramics which contain pores which are extended in 3D dimensions. Means it will like this. These are the ceramic foams. I hope you can clearly visible. These are the clearly visible part. Okay, these are the ceramic foams. See here. Here these pores are extended in different direction, and they are covered with solid part. These are the solid part. These are the solid part which are acting as the framework, and these all the voids are connected to each other. So they are ceramic foam. And here open cell and closed cell means, see, this one part which are surrounded by the solid framework is termed as one cell of that material. So that may be open because, see, this particular cell is connected to this cell, this cell, this cell, and this cell. So they are connected to its surrounding cell. So they are open cells. But there are some closed cells which can be because they are generated because of the cell wall. Actually, there are some porous ceramics where the solid part is forming as a solid wall between two cells. So they are generally, sometimes they are not connected to each other. So they are called as closed cell. Or sometimes it may be partially closed or partially open. So some material may contain both open and closed cell. So it's a mixed up of that. But just see that it is open, and when it will be closed, then this framework will act as the wall. Means there will be thin wall of solid material between two cells. Then it will considered as closed cell. Then these are the based on the geometry of the pores, how the pores are oriented in the material. So next is the based on pore size. Means see, this is a general classification. You will come across micro, meso, and macro. Micro means if the pore size is less than 2 nanometer, then this material is considered as micro. And if the material is ranging pores ranging in the range to 2 to 50 nanometer, then it is meso. And if it is greater than 15, that is macro. So it is a general classification of porous ceramics. And next is, okay, here I have put on slide on types of pores. This is actually for the first and second year students, because I hope third and fourth year students will know this portion. types of pores. See, here I am showing one material containing 3 types of pores. These are the 1 and 2 and 3. So types of open pores means they are open to one surface and they are open to another surface, means they are acting like channels connecting two surfaces. So they are called as open pores and channelized pore. And these two number are closed pores because they are surrounding by solid material and they are not connected with each other, and this channel like pores may be connected or may not be connected. And the last one is open pores with dead end, means they are open to one surface only and they have a ending point, they are not extended towards the other surface, so they have an ending point here, so they're considered as the open pores with dead end. So see, basically these all 3 types of pores have specific properties in different applications, because there are some applications where we will need open pores and there are some applications where we need closed pores only. So I'll come to that point. uh, but for the time being, see, these open pores are generally desired for permeability purpose or filtration purpose or any fluid infiltration purpose. But these closed pores are generally required for insulating purpose. Means if we want that heat should not pass from one portion to another, then we can keep that porous material in between, but that porous material should have pores of closed, because if it is not closed, then it may contain some amount of heat, conduct some amount of heat. Then next one is 3, and it may be helpful in drug delivery or any catalytic activity. So these 3 types of pores have significant importance in different applications. So next one is, so basically, these are the application part. Why do you need porous ceramics? Actually, so catalyst support, energy management, thermal insulation, sound absorption, fluid infiltration, biomedical application. These are some pictures I have taken from Google. Some practical application in our day-to-day life. See, first of all, this is a diesel exhaust, and diesel exhaust, I know, as you all know, in diesel automobiles or some vehicles running in diesel, they may the diesel exhaust may contain many impurity means they contain many polluting species in it, basically carbon. So before the exhaust enter to the open environment, they go through this honeycomb structure. See, this portion is porous ceramics, and it is honeycomb in nature, and they actually trap the particulates or trap the impurity phases into the structure, and so that the exhaust can be less polluting in nature than the previous. So this is a filter, it is application as a filter. So it is in the vehicle, we generally can see in vehicles, the diesel running vehicles. And next on, this is a sound absorbing porous materials you can see in theaters or any sound recording studio, where actually how they can absorb the sound, because when sound waves interact with the air present in the pores, they actually generate friction with the solids, and they transfer the sound energy into the thermal energy, and thus they actually absorb the sound. These are the porous ceramics which are used in the theaters or something, sound studio. And it is catalytic activity, because catalytic activity is due to the high surface area. It is because of high surface area, it has very pores and it has very high surface area, so catalytic activity can take place. And next on is, this is a biomedical, it is a synthetic bone. This is used in case of bone fracture or in bone replacement, and it is porous in nature. Why it is so? Because because for bone regeneration we need microcirculation of any body fluid in our body. So these are porous in nature, and when these are porous in nature, so there will be micro circulation of the body fluid, and as a result it will help in the growth of the bone or regeneration of the bone. So these are included in biomedical application, these are included in fluid infiltration and sound absorption. These are, and thermal insulation purpose is this type of bricks are porous in nature, and these are used in other countries for insulating purposes. Instead of using normal bricks, they use this type of insulating bricks for insulating purpose. So these are the some practical application of porous ceramics. So here the manufacturing part, how they are prepared actually. So see we, as you all got to know that porous ceramics are of two types, ceramic foam and honeycombs. So they are formed or manufactured as in different techniques. First of all, ceramic foam are uh, it is, I'm going in briefly, not in detail, so don't worry. These are the replication technique. Just know the terms. Replication technique, foaming technique, other technique. Replication technique is basically that we take a polymeric skeleton or polymeric porous material, uh, then we immerse that into the slurry, ceramic slurry, so that it coat the polymeric skeleton or polymeric porous material, and after combustion or after calcination, that polymeric material will burn out and it will result into a porous material. Like that, foaming technique is like where we insert some type of gases into the slurry or ceramic material, where it will form bubbles, and by using different additives, the bubbles can be stabilized, and the bubbles size are enlarged by using different additives, and then after drying or sintering we can get the final product of porous ceramics. Another technique is also that pore forming additives, where it actually uh, includes the use of carbonaceous material, carbonates, where it decomposes or chemically under chemical treatment they evolves different type of gases, and those gases can act as the pore former in that technique. So these are the ceramic foam. And honeycombs, actually honeycombs are very ordered and very symmetric in nature, and numbering up and extrusion are two types of technique that generally used in manufacturing of honeycombs. Basically, numbering up is that they are forming one tube and another tube, and they just combining all the tubes to get the unified structure. Let me show you. Okay. This part, honeycomb, means they are numbering up means they are manufacturing one tube, another tube. Then they are means they are combining all the tubes to get the whole honeycomb structure. This is called numbering up, and it is a very good for quality purpose. But it can be also manufactured by extrusion. Especially first year and second year students, I think they are getting in process ceramics extrusion. What is extrusion? But for first year there are some extruder, means one type of machine which used in ceramic formation purpose. Means if the consistency of the ceramic is paste, then we generally use this type of extrusion machine for forming of the ceramic material. So here in extrusion, they in the extruder, in the mouth of the extruder, they use some type of mold which have required porosity of the required. So they will form generally the porous structure like that, with uniform structure, uniform cross section, uniform porosity. So it is a very symmetric in nature extrusion purpose. So these four are some special type of technique that is generally used for formation of porous ceramics. First of all, sol gel. I guess everybody knows something, at least some basic about sol gel process and gel casting. Sol gel process, which includes basically alkoxide, metal alkoxide, and then polymerization and condensation takes place into the that solution, and basically at last, after extraction of this liquid, it will form some type of porous structure. Actually, when I will talk about mesoporous silica, I will talk about sol gel process, so don't worry about that. Actually, mesoporous silica involves sol gel process. So sol gel process basically we use when we need pores in the range of mesoporous range, means 22 to 50 nanometer, and then we use generally sol gel. It is uh, very much important. And the next is gel casting. Gel casting means actually it's a type of sol gel process, but here actually the strength of the material is higher than in compared to sol gel. And next is wood ceramics. As name says, wood ceramics means um, as you all know that every plant or every tree have porous architecture in it. So people they mimic the uh, porous architecture of the wood. Generally they take the porous skeleton of the wood, and they coat them with ceramic material to get the porous architecture of the wood. So generally, first of all, we take the wood, and we burn that organic material from that wood portion, and then we will get a carbonious skeleton. And that carbonious skeleton we can coat them by using some liquid ceramic material or some gases to get the desired porous ceramic material. So this is a special case of a special fabrication technique, and that is glass form. As name suggests that it will be glass, because see, they take glass powder and some foaming, means pore forming additives they basically include. And definitely actually pore forming means they use some carbonates or carbonaceous material, and when they heat treat that mixture, means glass powder and foaming or pore forming material additives, in high temperature heat treatment, the pore forming material will decompose, or due to some chemical reaction they will evolve many gases in the structure, and they will generate a large amount of pores into the structure. So these are some special type of, and these are some general techniques for how porous ceramics are generally manufactured. And next is see, this portion was actually for a brief introduction about porous ceramics and why and in which application we are using this porous ceramics in our day-to-day life. It is covering this portion, and and this is the my special type of porous ceramics. This is mesoporous silica. Where see, mesoporous, as I have already mentioned, mesoporous means the pore size will be 2 to 50 nanometer. So mesoporous silica is a form of porous silica which have pores in the range of 2 to 50 nanometer, and it is one of the most remarkable development actually in the domain of, especially in the domain of nanotechnology. Nowadays, many have worked on this, and many are working on this actually, mesoporous silica. And what are the unique properties which make them unique from other porous ceramics? These are tunable ordered pore structure. The pore structure of the mesoporous silica are very much ordered. I'll show the pictures. And then control porosity. Means they have we can control the porosity of the material by altering the process parameters. And what are the process parameters, I will go to that point. And High specific surface area, of course, as you all know that if material have large pores, then that will have high specific surface area. And one of the most and important, this one is the possibility of synthesis in a wide range of morphologies. Actually, mesoporous silica can be manufactured or can be produced in a different type of morphology. And what is morphology? It is very important. So I'll go for that. Morphology is shape, means for first and second year, just imagine it as a shape of the material or shape of the nanoparticles mesoporous silica, the shape. So wide range of morphology means they can we can generate different shape of the mesoporous silica by varying or by using different processing parameters or by adapting different processing factors. So next is mechanical and hydrothermal stability, and this one is good because we are using the manufacturing process which we are using, or many people have worked on this using sol gel process. They involve actually hydrothermal, means they involve thermal high temperature, quite 80 to 150 something. So high temperature, so as the mesoporous silica are very much stable in hydrothermal conditions, so it's quite easy in manufacturing in that technique, that is hydrothermal sol gel process. And next one is flexibility in operation and surface functionalization. See, as I have already mentioned, the manufacturing process is quite interesting and quite easy, though. And so it is very flexible in operation. We can alter the pH of the solutions, and we can get different morphology. If we alter the amount of solvent or amount of reactant or amount of silica source we are using, then we can get different morphology, and as well as we can get different results. So it is very much quite interesting about that. So these are the properties which make them unique from others. So, and the surface functionalization is means adding some just in simple word, adding some cationic or anionic group on the surface of the mesoporous silica. It is very easy for that, using some chemical treatment or using some grafting technique. We can adhere some type of cationic or anionic group, functional group on the surface of the mesoporous silica, and it actually enhance the properties of the mesoporous silica. And many people have worked on that functionalization, and it has showed very good results actually. So mesoporous silica actually have different types, means they have families of this uh, KIT, FDU, MCM, SBA. MCM, SBA, these are the families of mesoporous silica, and specifically many have reported on MCM and SBA, and these are the short form of the institute from where they have originated initially. They are the short form, and people actually know them as in the short form only. And basically, MCM and SBA, SBA 15 are very much important, very much famous, because many people have worked on this, and they have showed very good result, specifically in the application of absorption field. So and they have showed very good enough result. So these are the this quite introductory part of mesoporous silica. And next one is types. Same, I have already said that it has different types of families of mesoporous silica. So what makes them different from each other? Generally the pore geometry. Actually this figure actually not showing it clearly, but just see this. Actually, different families of mesoporous silica will have different pore geometry. It may have 2D hexagonal, it may have 3D cubic, and it may have laminar type. So depending on that pore geometry, pore size, and people have named them as different family. And these are the basics. Just for a clear view, I have taken this from a paper, research paper. So these are the types of Mesoporous silica. So next one is say, and here I have already mentioned that one of the most important and remarkable unique point of Mesoporous silica is that it has showed many various types of morphologies, and it's quite interesting. See, for a particular Mesoporous silica, it can show uh, rod-like shape, and it can show spherical-like shape. It can show platelets-like shape. It can show this flower type or popcorn type shape, and this can be fiber type, and this can be worm-like. Different various of morphologies, and this morphologies results as the alternating of the processing parameters. And what are those processing parameters? I will go to that point. Means if we are manufacturing it, as I have already mentioned that we will in the manufacturing process we just include some solid process in hydrothermal condition. So in that hydrothermal condition, we are using 40 to 150 temperature, and so if one people are getting spherical in nature in 80-degree or 90-degree, other may get platelets like morphology in 150 or 140. So altering the various temperature, pH of the solution, or other processing factors, we can get a number of quite different numbers of different types of morphologies. And see, one important factor I want to mention here, that many have reported that the rod-like structure of the Mesoporous silica shows a very good result in absorption capacity, rod-like structure, or not absorption, and this platelets also, because due to this platelets, because due to this high surface specific surface area platelets, they shows high absorption capacity, and this pores and this rod-like structure also shows a very good absorption capacity of different materials or different impurities. So next one is application part. See, it is a type of porous ceramics, so obviously it will be like it will have environmental field. In environmental field, it will have absorbent. It will act as catalyst. And in biomedical drug delivery, bone regeneration, I have already mentioned that bone regeneration, they will have porous structure, and this porous structure will help in microcirculation of the body fluid, and which will help in bone regeneration basically. So in catalyst support chemical analysis, then functional device sensors means see, I have talked about the functionalization, that we can adhere some type of cationic or anionic group on the surface of the Mesoporous silica, right? So this group can enhance the performance of the Mesoporous silica in the field of sensors. They can sense some chemical species or some other signals. So in the solar cell too, they are they are actually enhancing the performance of the solar cell by reducing the reflection, means specular reflection, reducing the specular reflection. They are enhancing the performance of the solar cell. And nanoparticles and nanoarray, and these are the some of the application of Mesoporous silica. And it is quite see, for the absorbent purpose, they are basically used in quite large number, because pure water and purification technology, water treatment technology, Mesoporous silica plays a very important role. And so people are working, and people are generally trying to manufacture Mesoporous silica in a quite good amount, so that they can use them in a large amount in the field of purification technology, because But there is a problem. I'll mention that problem. What is the problem about the manufacturing of mesoporous silica? Actually, it is about the raw material that we use for the manufacturing and silica source. These are the application part. This is synthesis method. Manufacturing method is same. CTEP is here. CTEP is a surfactant. First of all, let me. Okay. Manufacturing process, this is basically this process, whole process is a sol gel process. Sol gel process, I hope everybody knows. Just a brief about sol gel process. This is all this is a basically sol gel process involving under hydrothermal condition. So here, first of all, surfactant is used. As you all know, the surfactant will have a hydrophilic part and a hydrophobic part. So these are the individual molecule of CTEP. CTEP is a surfactant used basically for Mesoporous silica, and it is very commercially available. So then it will take a micelle formation. Micelle formation when basically micelle forms when the concentration of the that CTEP will be higher than the concentration, critical micelle form concentration. So micelle will form. Micelle means, see, this arrangement of the CTEP will called as the micelle formation. Then when the concentration of the CTEP will increase, then it will take the structure like this, like rod like structure. Then when it will increase, then different types of rod will accumulate it, or they will they will assemble like this structure. And when we are adding the TOS, TOS is the titrile orthosilicate. This is the silica source. Actually, we are manufacturing silica, so this is a silica source, TOS. So tetraethyl orthosilicate is a very expensive silica source. So people are trying to get some cheap source or a very low cost source of silica. They are trying to get to manufacture mesoporous silica industrially or in large scale. So adjusting the pH of the solution and adding the silica, actually adjusting the pH, then the silica particles will accumulate or precipitate or condenses on the surface of that micelle. And then after aging or further condensation, they will take this structure. See, this is the micelle or rod same micelle, and above there is a precipitation of the silica particles or silica particles on that shape. Then after removal, so if we remove this surfactant, that will take this shape, the shape of this porous structure. So this surfactant removal can be done by chemical treatment sometimes, or can be done by basically as it is a hydrothermal process. So generally it is heat treated or calcination is done to remove the surfactant, and we at last we get this type of structure. And see, this is the ordered mesoporous silica. I have already mentioned that it is a it has very unique properties, that it has ordered porous structure. These pores are very ordered, very regular in nature. And and the shape of the pores or size of the pores depends on this micelle formation. What amount of CTEP or surfactant we are using, and how much amount of silica source, this TOS, we are using or adding, and what are the alkaline pH of the solution medium. Because as we increase or decrease the pH, the precipitation as we decrease the pH of the solution, then the precipitation rate will be different from the pH at another level. So this is a basic sol gel process, and this is a generalized hydrothermal process for the manufacturing of mesoporous silica. So see, this is a manufacturing process, and I have mentioned the processing parameters like concentration of the surfactant, and then what type of surfactant you are using, then how they are assembling, and they are what is the pH of the solution, and what is the source of the silica. This is very important. What is the source of the silica, and how much amount you are adding, and how they are precipitating on the surface of the solution, and how much temperature you are using for the removal of surfactant. All other processing parameters which are very important to get the desired mesoporous silica with desired morphology. So if you alter, or if you vary if one or two factors processing parameter, then it will result a different morphology or a different mesoporous silica with different porous architecture. So this is the synthesis method of Mesoporous silica. This this is future scope. I have completed the part of Mesoporous silica. So this is a future scope and importance. High order Mesoporous silica ordering processing. See, I have already mentioned it. There are very different types of processing parameters which actually determines the porous architecture or morphology of the Mesoporous silica. But one of the most important processing parameter is silica precursor. Uh, so many people are working on that. As I have already mentioned, TOS, triethyl orthosilicate, is a commercially available silica source, but it is very much costly. So we cannot use it in the industrial scale or large scale. So people are working on the low cost silica source, and many have resulted many have showed the result uh, in a very good positive way, because see, this low cost silica sources can be rice husk, quartz, fumed silica, colloidal silica, bagasse ash, sad ash, and cenosphere. So these are some very low cost silica rice husk. As you all know, that these are the byproduct of the rice paddy or something. So they are just wastage, we can consider as wastage, and so we can reuse them for the to get the silica, because rice husk is a very rich in silica and carbon, silicon and carbon, so we can use them as the silica source. And many papers, many people have worked on that, and they have got many good result, and actually they have showed results which are quite comparable with the Mesoporous silica using TOS, commercial available silica precursor. So we can work on further on the rice husk, and as my final year project, I was working on rice husk as extracted silica. But now I'm actually moving to another portion. I'm working on silica now, because of the because we, in our department XRD machine is not installed yet. So so I have completed my presentation. Wait a minute. Thank you. And do you have any question?